Welcome back, everybody. In our last video, we talked about what a Taylor series and Maclaurin series are. That we can take a perfectly good function that's just minding its own business, not hurting anybody, and if it has derivatives that we can take, like you see there on the screen, we could write it as a power series. Why we might want to do that to a poor unsuspecting function is a different question, and we'll get to that in a different video. But if we have a function and we want to turn it into a power series, this is the only way to do it. If we want a power series centered at some point C, and again, that'll be a number that we have to know. Somebody will tell us that number ahead of time. Or they'll say, find a Maclaurin series, which automatically means we're doing C equal to 0. We'll take that number C, take a bunch of derivatives, plug that number in to the function for all these various derivatives, and there's our formula for how we write it out. So let's do it. So we saw in the very beginning of the last video, and actually a video in our section on power series, how to write or not how to write e to the x as a power series, but the fact that we could. So let's check and make sure that we get what we think we get. Let's find the Maclaurin series for e to the x. So again, Maclaurin series means c equals 0. That's the only difference between a Maclaurin series and a Taylor series. Remember that a Maclaurin series is just a special kind of Taylor series, right? One where c is equal to 0. Just like, Corvette is a special kind of car. It's the same relationship. So what do I get if I take the kth derivative of e to the x? Well, no matter how many times you take the derivative of e to the x, it's always e to the x. So all the derivatives of e to the x are just going to be e to the x. When I plug in 0, what do I get? I get e to the 0, which is just 1. So the kth derivative of e to the x will always be 1. So there's my formula, right? I need the kth derivative of e to the x with 0 plugged in. That's this first part here of my coefficients, right? The kth derivative with the point that I'm centered at, which in our case, because we're doing a Maclaurin series, is 0. So right here goes a 1. Then below that is k factorial. That's easy enough. Then I'll have x minus 0, in our case, raised to the kth power. In other words, just this, 1 over k factorial, x to the k. We sum that up from 0 to infinity, and there we go. That's the Maclaurin series, the Taylor series centered at 0 for e to the x. So now we've taken a perfectly good function, e to the x, and I've turned it into a power series. And we call that its Maclaurin series because it's centered at 0. That's awesome, right? We'll find out very soon what we can do with that. But before we go, using this, let's keep practicing turning other functions into series. So here's cosine. So we want to find its Maclaurin series. So here I'll put the formula there on the screen so we know what we're looking for. We need to find these coefficients. That's the big thing, right? This part in red. The k factorial, that's easy enough. That's no real work. It's just k factorial. The hard part is finding these derivatives and plugging in c. And again, if I'm finding a Maclaurin series, then c is equal to 0. So I need to find all these derivatives, the first derivative, second derivative, third derivative, kth derivative, and plug in 0. And that's all I have to do to figure out what these coefficients are, and I can write out its Maclaurin series. Okay, how do we do that? Well, mercifully, right, cosine is pretty easy because there's a nice pattern to its derivatives. So we start out with the 0th derivative, which means the function itself. When I plug 0 into cosine, I get 1. Okay? We have to think back to, to trig a little bit, but cosine of 0 turns out to be 1. Now we take the derivative of cosine. The derivative of cosine is minus sine. I have to plug in 0. So f prime, when I plug in 0, gives me negative sine of 0, and that's 0. Okay, cool. Second derivative. Derivative of negative sine would be negative cosine. So I plug 0 into that, and I get minus 1. Then I take the derivative of minus cosine. Well, that's 2 minus signs show up now, so I'm back to positive sine, which is still 0 when I plug in 0. So awesome. What about the fourth derivative? Well, here's why we're doing cosine as an example, because the fourth derivative The derivative of sine takes us back to the top to cosine. So we get this pattern, right, where the derivatives will go 1, 0, minus 1, 0, and then start back over at 1 again. Right? Because the derivative of cosine goes through this cycle of 4. So it's pretty easy now to start writing out our derivatives. And, well, there's the derivatives. To start writing out our series. So as we have here in blue, right, we just need to write out these terms. What you would expect to see in the homework and on an exam is two kinds of questions. One is write out the first, 5 or 6 terms, right, of a series. The second is use what you know about some series, like the one we're doing for cosine, the one we just did for e to the x, and manipulate that to try to figure out the series. So we'll do some examples of those later. But this process we're doing now, usually you won't have to try to guess the pattern, which we're going to be able to see because there's obviously a pattern to the derivatives. We'll just be able to just write out the first 5 or 6 terms in the homework. For us, though, we can write out all the terms because we can figure out what the pattern is. And here we go. So first we need f of 0. Well, that's 1. Then we need f prime of 0. Oh, that's 0. So I'll have 0 times x to the first power. Then I need the second derivative, right, divided by 2 factorial. And I plug 0 into that second derivative, which of course gives me negative 1. So I'll get negative 1 over 2 factorial and then x squared. Again, why not x minus c? Remember, we're doing the Maclaurin series, so the c is 0. Okay. Next term, I need the third derivative. Of course, the third derivative is 0 when I plug in 0, so I just get 0. Okay. Now we're back to the top again, right? The fourth derivative, right, that's just 1 when I plug in 0, so I get 1 over 4 factorial x to the fourth. The fifth derivative, well, when I plug in 0, I get 0 again. Okay? I bet you can guess what comes next. The fifth derivative was 0. The sixth derivative is going to be negative 1 when I plug in 0. So I'll have negative 1 over 6 factorial x to the sixth, and so on. Because you see what's happening. All the odd powers of x have a 0 in front of them. So those are just 0. All the even powers, right, are alternating signs from plus to minus, plus, minus, and so on. So could we figure out the pattern here and write it in a nice way? The answer is yes, but maybe it's not completely obvious. So how do I write x raised to even numbers, right? So because what I need here is x raised to the 0th power, second power, fourth, sixth, and so on. Well, the trick to get a sequence that just gives you even numbers is you write 2 times k, because 2k will count as k goes 1, 2, 3, 4, 5, 6. 2k goes 2, 4, 6, 8, 10, 12, right? Or actually, yeah, 0, when k is equal to 0, then 2, 4, 6, 8, 10, 12. So I use that, right? I'll have 2k as my power and also 2k as my factorial. And then my derivatives are just plus 1, minus 1, plus 1, minus 1, and so on. So I get negative 1 to the k, because that's how you get plus, minus, plus, minus, plus, minus. Then my power is just the even numbers, and I'm dividing by the even numbers factorial. That's my pattern. Now, on an exam or on the homework, do you have to guess the pattern? No, because usually there's not a nice pattern, and usually it's not something that you can figure out. But for cosine and for sine, in just a second, there's an obvious pattern, and I'll just tell you how it works. But you do have to memorize this formula, because there'll be lots of examples, we'll see some of later, where you might want to find the Maclaurin series for, say, 3 cosine of x to the 4th power. And if you know the formula for regular old cosine, how to turn it into a Maclaurin series, we can use that. So, do you have to be able to figure out the pattern? No, you'll just have to be able to write out the first few terms, like I did there at the bottom of the screen. Guessing the pattern is something that I will tell you. Okay? But let's try sine. Okay? So here's what we're looking for again. All these derivatives, we're finding a Maclaurin series, so we need to plug in 0 and divide by the k factorial. So same sort of thing we had before, only it shifted by a little bit in the cycle. So the function is sine, so when I plug in 0, I get 0. The derivative of sine is cosine, so I plug in 0 and I get 1. The derivative of cosine, well, that's negative sine, but when I plug in 0, it's still 0. It's the third derivative, when I take the derivative of minus sine, that I get minus cosine, and I plug in 0, and that turns into minus 1. And you see how it's going to repeat again, because the derivative of minus cosine takes me back to the top as regular old sine. So, same thing happens again that we did last time, right? We start writing out the terms. What is f of 0? Well, that's 0. Right? What's f prime, right, of 0 divided by 1 factorial? Well, f prime is 1 divided by 1 factorial is 1 times x to the 1 power. X squared, the x squared term, the next one, is going to be 0 because the second derivative is 0, right? Third derivative is negative 1, so I'll have minus 1. Then I'm dividing by, of course, 3 factorial. Right? The third derivative with 0 plugged in, divided by 3 factorial times x cubed. Next term, that would be the fourth term. Right? That's what I get when I take the fourth derivative, but it's 0, so I'm going to get 0 again. Right? Next time I'll have, that's right, plus 1 over 5 factorial x to the fifth, and so on. Next time would be 0. Next time would be negative 1 for the derivative with 0 plugged in, divided by 7 factorial x to the seventh, and so on. So now how do I write as a formula down here odd numbers? Because for even numbers I did 2k. For odd numbers I do 2k plus 1. That way, as k goes 1, 2, 3, 4, 5, 6, or better yet, 0, 1, 2, 3, 4, 5, 6. 2k plus 1 goes 1, 3, 5, 7, and so on. Okay? So I'll have x to an odd number divided by odd number factorial, and then my derivatives again are going plus minus plus minus plus minus. So I get negative 1 to the k. So again, you don't have to figure out the pattern for the homework. You just have to do what we did here and write out the first several terms. Or you might have a question where you have to know this formula. So this is a formula that we'll have to know. So one quick comment before I summarize all of this for you and give you a screen of things that you have to have memorized. One thing you might notice here is sine has only odd powers in its Maclaurin series. And if we go back a step to cosine, remember that it only had even powers, right, in its Maclaurin series. So does that strike anybody as weird? Well, remember, it's not weird if you remember that cosine is an even function and sine is an odd function. And so part of the reason for the name comes from exactly this fact. Even functions only have even powers in their Maclaurin series, and odd functions only have odd powers in their Maclaurin series. Okay, so let's summarize what we've done so far, and let me give you a screen full of stuff to memorize. So if you have a piece of paper handy, or if you want to mark this, you can come back to it later and write all this down. This is stuff that you have to know for the exam. So first thing is the dark magic formula that we talked about before, right? How do you take a function and write it as a series? And you have to know this pattern. It's not really a formula, really, right? So much as just a pattern of taking derivatives and dividing by the appropriate factorial, just like we did for e to the x, and for cosine, and for sine. Because what you'll see in the homework is they'll ask you to do the same thing for a square root or for a log, and you have to be able to use the same pattern, right? And if you don't know the pattern, then you can't do it at all. So we have to know this. The other 4 things we have to have memorized are these Maclaurin series. So the Maclaurin series for e to the x, for sine, for cosine that we just figured out. And then one more down in the left-hand corner there. We didn't work this one out, but we actually already knew this one. 1 over 1 minus x. Remember, that's the formula for a geometric series. Right? The first term is 1. That's what you get if you have the series just k equals 1 to infinity, x to the k. Now if you check and start taking derivatives, you'll see that the derivatives with 0 plugged in is exactly k factorial. So this first term cancels and you just get 1 there. The first 3 that we did, e to the x, Cosine, sine, those all have radius of convergence equal to infinity. They converge everywhere. This last one is different. It only converges, well, it's like a geometric series, right? Its radius of convergence is 1. It only converges between -1 and 1.